confirm whether you can hear me now. I think my audio developed a problem and I need to be checking it now and again, and if it has an issue from the other end, kindly let me know if you can hear me. Yeah, we can now. Great. Jasmine, thank you so much. Is this okay for AQ as well? Mostly the physics concepts are quite related, but this is much curated for the GCSE Paper 2 students. I cannot tell you that this is physics is not any different. The concepts are just the same. Yeah. All right, so let's get started. Let's get started from the first part. I was looking at this question and I said this paper is having 100 marks. GCSE Paper 2 H is tested 100 marks, and this is 1 hour 45 minutes. And the first question that I was looking at here, before my audio developed that issue, I was saying that if you have a magnet, and then you also have a coil. In the event, if let me just getting a paper so that I can be able to illustrate this on exactly what we are trying to say here. Let me just illustrate this so that I can be able to understand what I'm trying to say at this given point. So we have coils here. Now assume we have these coils here. I have different coils there, and then I have a magnet. I'm inserting a magnet into that coil back and forth. So something that we need to realize is that this magnet has got what we call the magnetic fields. Yeah, so this magnet has the magnetic fields which are pointing from the north to the south like that. So which means when you are inserting the magnet in and out of the coil, the magnetic fields are going to cut through the coil. And when magnetic fields cut through the coil, an EMF, or a potential difference, is induced in the coil through electromagnetic induction. So something that we really need to take from this live today is that whenever a magnetic field cut through the coil, cut through a conductor, an EMF is induced in that particular conductor where the magnetic field is cutting, right? And when that happens, a current flows. So in this question, we are told, explain what will be observed on the on the meter when the magnet is pushed in and out. The meter is going to deflect due to the flow of electric current. So the meter will deflect, and this deflection is due to the current that is detected. And why is current detected? When the magnetic fields are going to cut, or when the magnet is going to be pushed in and out, these fields here are going to cut through the magnetic fields are going to cut through the conductor or the coil. And when the magnetic fields cut through the coil, an EMF, or a potential difference, is basically induced in this particular coil, which is going to result to the flow of current. So the EMF is induced through electromagnetic induction. And also you need also to realize that the direction of the current induced depends on the direction, or depends on the direction in which the magnet is moving. So when the magnet is moving in, the current will flow in a particular direction, and when the magnet is moving out of the coil, the current is going to flow in a particular direction. So basically that's why I need to add a statement here and say that as the direction of the motion of the magnet changes, the direction of the current also is going to change. Yeah, so basically that's what we are supposed to do in this particular question. And I need also to mention, suppose they ask you a question, how can you be able to increase the amount of current induced? To increase the amount of current, there are a few things we're going to do. Number one is using more number of turns, also, or using a stronger magnet, or you can also increase the speed at which you are moving that particular magnet in and out of the coil. Yeah, so basically that's what we're going to do. Then we're going to move to the next question, and this question we're going to talk about transformers. So I need to check in the chat section if there is anything mentioned. Yeah, if somebody left a message there. There is an alternating current of 3 amperes in the primary coil of a transformer, and there is an alternating current of 6 amperes in the secondary coil of a transformer. The transformer is 100% efficient. When you are saying a transformer is 100% efficient, what we mean is the power in the transformer is equals to the power out of the transformer. So which will mean that in the event you have power in the primary coil, then we're going to say is equals to the power in the secondary coil. To the power out. All right, so the size of the potential difference across the secondary coil is, so what happens here, we are going to use the formula current in the primary coil over current in the secondary coil should be equals to voltage in the secondary coil over voltage in the primary coil. Or you can also look at this from power in is equals to power out, from the concept that has been mentioned here, that the transformer is 100% efficient. So which means power in the primary coil is equals to power out of the power in the secondary coil in that case. So of course we can be able to focus now on this first equation that we are given there, and we can say the current in the primary coil is 3 over 6, which is the current in the secondary coil. Now we are trying to find the potential voltage across the secondary coil, so we can be able to say this is VP, so we can be able to rearrange and make voltage in the secondary coil the subject, and you can see voltage in the secondary coil is going to be a half the size of that in the primary coil. So basically that's what we are going to do here, and we can take that to be option that is option it's going to be D. Yeah, so this is going to be D, and that becomes our answer. All right, and the next part, another formula that you really need to remember as far as this area is concerned is voltage primary coil over voltage secondary coil is equals to the number of turns in the primary coil over number of turns the secondary coil. All these formulas, they are provided, so we are not going to cram these formulas in order to answer them. We are told to explain, we are supposed to explain how an alternating current in the primary coil causes an alternating current in the secondary coil. This is a question that is asking you to explain how a transformer works. So the first thing that we need to remember is that a transformer works with alternating current. So which means that for a transformer to work, there must be some magnetic fields which are created. So which means that when current flows through the primary coil, let me just draw a simple illustration. Let me just draw a simple diagram of how a transformer works. And what you need to remember that the main features of a transformer is the primary coil and also the secondary coil, whereby the primary coil is the input and the output is the secondary coil. So that means yeah, so that means also we have a soft iron core. So when alternating current flows through the primary coil, we're going to realize that magnetic fields which are constantly changing size and directions are going to be created. So these changing magnetic fields are the ones that are going to cut across the secondary coil. Once there is an alternating current in the secondary coil, yes, this is F. So I thought you said you are going to go over generator and the motor effect yesterday. Yeah, I'm going to go through that. This is electromagnetic induction, and then there are questions. It's on the way. We're going to look at it. F. Mr. F, how are you? Welcome to our live. Welcome, bro. Yeah, we shall look at that area. Yeah. Yeah, so once that happens, then these magnetic fields which are created, when they cut across the secondary coil, this is for Edexel, yeah, twist, this is for Edexel, yeah, this is Edexel 2H, yeah, not AQA, this is not AQA. When the magnetic fields cut through the secondary coil, so what's going to happen is that an induced EMF is going to be created in the secondary coil. So when the created magnetic field, because we have said in the primary coil we're going to have alternating current passing through the primary coil. When that happens, they will create magnetic fields which are constantly changing size and direction. When these magnetic fields cut through the secondary coil, an EMF is induced, an alternating EMF is induced in the secondary coil, which is going to result to a flow of current. Basically, that's what you are going to say as far as this particular question is concerned. Is induced through electromagnetic induction. All right, so I think I need to move this a little bit up so that you can be able to have everything well stated there. So if you are going to meet a question to do with transformers, kindly guys, just crush it, twist. Good luck. Wish you all the best, you guys who are live here. All the best in your exam. So I want us to move to the next question. Of course, we are having here a soft iron core. The iron is used to make this soft iron core, and the coil is made of copper because copper is a good conductor. Yeah. The primary coil of a different transformer is connected to 230 volt main supply. The voltage across the secondary coil is 15 volts. The primary coil has 600 turns. We are supposed to find the number of turns in the secondary coil. So we are going to use the formula that is usually given, Vp over Vs, where voltage in the primary coil over voltage in the secondary coil equals to number of turns in the primary coil over number of turns in the secondary coil in that case. So which means if we substitute and we try to make number of turns in the secondary coil, the subject, we can be able to work it out. And if we work it out, our answer becomes 39 turns. 39 turns. Now we have also a generator. Shows a coil of wire that is being rotated within the poles of the magnet. This is the generator Mr. F was talking about. And what is the purpose of the generator? The generator generates electric current. And under which mechanism does it generate current? Is through electromagnetic induction. So what we need to understand as far as this concept is concerned is that when a conductor cut through a magnetic field, because in this part here we need to appreciate that we have two magnets. We have the North Pole and also we have the South Pole, and then we have the magnetic fields which are just pointing from the north to the south. Yeah, these fields are pointing from the north to the south. So we need to also appreciate that when the conductor cut through the magnetic field, because this coil is going to rotate within the magnetic field, when it's rotating within the magnetic fields, when it's cutting through the magnetic fields, when that coil is going to rotate within the magnetic fields, it's going to cut through the fields. And when a conductor cuts through the fields, an EMF is going to be induced in that particular conductor. And that is how electricity is generated, because we have a coil that is turning within the magnetic field. As it's turning within these magnetic fields, it's going to cut through the magnetic field. And when a conductor cuts through a magnetic field, an EMF is going to be induced. Okay, so there's no need, Saudi school 140 mg, there's no need for you to be cooked once you have joined ProfLearn live. You are not going to be cooked on this. I'm not going to allow that. All right, so what I'm saying is, when the coil is going to be rotated within the magnetic field, that particular coil is going to cut the field. And when a coil cuts through the fields, then what we're going to have is an induced EMF in the coil, which is going to result to the flow of current. So I'm going to write how you are supposed to structure your answer in this case. So we are going to say, as the coil moves, it cuts through the fields. So as the coil is going to move through the is going to rotate within, it's going to cut through the fields, and the fields of the permanent magnet, that's going to cut through the fields of the permanent magnets, then, which will mean that an EMF is going to be induced. Yeah, great. So we agree on that. If you are writing down, you write how a generator works. As the coil moves it cuts through the fields of the permanent magnet, and the voltage is induced in the coil when it cuts through the varying magnetic fields. So the amount of EMF induced depends on Cookie Monster. Hello, how are you? Welcome. The amount of induced EMF depends on the angle at which the conductor is cutting, and also it depends at the rate at which the conductor is moving, and also the position. So when the coil is cutting perpendicularly, maximum EMF is going to be induced. But when the coil is parallel to the field, there will be no induced EMF. So that's why I'm saying the size of induced voltage depends on the rate of change of magnetic field and the angle between the magnetic field as well as the direction of movement. The greatest rate of change is when the coil is moving perpendicularly. Is going to be when it's moving perpendicularly. Cook Monster, this is a Dexel, not AQA. Right. So at this particular point, that's where we have the maximum. Yeah, maximum. And at Q, that's when the object is the coil is moving perpendicular. The field, the motion of the coil is perpendicular to the direction of the field. Yeah, and we are going to say therefore, yeah, the greatest rate of change occurs when the coil is moving perpendicular to the fields, and that is going to happen at point Q and S. At point Q, that is where we are going to have maximum induced EMF, and when the conductor is moving parallel to the field, so the maximum current is at point Q and S. And when the conductor is moving parallel to the fields, then it means Cookie Monster, good luck, see you guys. And then we have, and the currents are moving in opposite direction, so that's why you can see Q is that positive highest point and S is the lowest point, is because the currents are moving in the opposite direction, but that's when we have the maximum. And the next part is to identify no current is induced when the coil is moving parallel to the fields. So that's what I'm saying, that when the coil is moving parallel to the field, and that occurs when the coil is vertical. When the coil is vertical, there will be zero current induced, and that is going to happen at point P, R, and T. So P, R, and T, the coil is vertical. Yeah, so that's when it will be it's vertical, so it will be rotating like that. But when it's horizontal this way, the field will be moving across that way. Then when it will be rotating, the direction of motion of the conductor is going to be perpendicular to the fields which are across. So Q and S, the coil is horizontal. That's when it will be rotating like that. When it reaches the vertical position, the coil will be moving parallel to the direction of the field, and in that case there will be no induced EMF in that case. So this is parallel, this is perpendicular, and then this is perpendicular as well. So basically we need to say this is going to occur at PR and what? T. So the coil is vertical position at these particular points. Now, in the event you are asked to state how you can be able to achieve a higher amount of current induced, something that you need to do there is to increase the strength of the magnet or increase the speed at which the coil is rotated within the magnetic fields. And also we can talk of having more number of coils. That's how you can be able to increase the amount of EMF induced. Question number 10. Also in electromagnetic induction, we are told the figure shows a bar magnet that is dropped through a coil, and the coil is connected to a sensitive meter. So you can see we have a magnet at the top, and this magnet has magnetic field. So when it's going to drop, these magnetic fields of this permanent magnet are going to cut through the coil. And when they cut through the coil, an EMF is induced in that coil, which the meter detects. Yeah, so basically that's what we're going to have there. We are saying that this magnet is going to drop, and in the process of dropping, these magnetic fields are going to cut through the coil, and then there will be an EMF induced. So we can put it in words and say, for safety and security purposes, that as the magnet falls through the magnetic field, the fields cut through the coil. Cuts to the coil, and an EMF is inducing an EMF or inducing a voltage, which is going to result to the flow of current, and then that is going to be detected. So the meter is going to detect that amount of current that flows through. So basically that's what we're gonna say in that particular part. And this induced EMF is induced through electromagnetic induction. All right, so we are saying that the magnet falls as the magnet falls through the magnetic fields. As it falls, the magnetic fields cut through the coil, inducing an EMF. inducing a current in the coil and through electromagnetic induction. Hence, there is a potential difference across the voltmeter, and the voltmeter measures that potential difference, and that's why